Okay, welcome back. Today we're going to look at homogeneous equations and techniques of integration, which I feel that you probably need some practice with, given that my experience in teaching Math 201, some of the students there didn't have a lot of experience in basic integration techniques. So considering that many of these differential equations problems require some strong integration skills, we're going to spend a bit of time revising some of that material today. Okay, so let's jump into it. Homogeneous equations that are first order. A first order ODE, y dash is equal to a function of both t and y, where the y dash derivative is dy on dt. This is said to be homogeneous if for all real non-zero values of s, f of st comma sy is equal to f of t comma y. So your first step in recognizing whether you have a homogeneous ODE is to just test whether, if you substitute in a variable s next to the t and next to the y, can you cancel that s in the equation to determine that that's equal to f of ty. And then your second step is to actually solve the resulting ODE using the techniques that we discussed below. So that would be to set out a letter v and say y is equal to t times v, or v is equal to y divided by t. So now let's first differentiate this using the product rule of differentiation. So we have y dash, so the derivative of y with respect to t is equal to just substituting, replacing the y for t times v. So we have the derivative of tv here. Now using the product rule, we separate that as a sum of v times dt on dt, or the first one in that product. And then we swap that around and add the result together. We add t times dv on dt, and then we want to simplify this. So dt on dt is just 1. So we have v plus t times dv on dt, or v plus t times v dash of t. So we claim now that the result is a separable ordinary differential equation in v and t. So let's have a look as to why that might be. So far we've established that that y dash is v plus t times v dash. Okay, now our ODE is y dash equals f of t comma y, and then if we then replace y with tv, then we've now established that v plus t dv on dt is equal to f of t comma tv, and we claim that this is separable, and so therefore we can use techniques of separable ODEs to solve that equation. Okay, so let's have a look and see why this is separable. So notice that the ODE is homogeneous. Since the ODE is homogeneous, we can put s is equal to 1 on t. So up here we can say let our s be just 1 on t, and we let y equal to tv as we've done above. So f of 1 comma v is the same as f of 1 on t times t, where here we've got our s being equal to 1 on t, and then the second part of that is 1 on t times y. So just what we've got in the top line here with s equal to 1 on t. Okay, we simplify this. So simplifying what's inside the bracket, t divided by t is 1. So that's how we get the 1 in the first part of that. And the second part is y over t, which is actually just v, according to the way that we defined v up here. So this is why that's f of 1 comma v. Okay, now because of that homogeneous property, we can pull out that 1 on t, and we have that this is the same as f of t comma y, right? Which is the same as y dash of t, since that's the way that equation was recognized in the beginning. Okay, so y dash of t, remember now that this is just, according to our calculations using the product rule, this is v plus t times v dash of t. Okay, so we'll see that this is separable because we can separate and put the v's with the v's and the t's with the t's and integrate the result. So let's move on and look at the next page. So we can, so what are we doing here? We are taking the v over to the left-hand side, and then we will have f of 1 comma v minus v. We will divide both sides by that result and just rearrange and separate this. So let's have a look then. We get dv over f of 1 comma v minus v. So that's with the v's collected, and then we divide both sides by t, and we have 1 over t, or t to the minus 1. And then we apply the integration symbol and actually integrate those. All right, so this actually gives us a formula here in equation 2 for what to do when we have recognized that we have a homogeneous ODE and we've set out a v, we know our f, so it becomes pretty simple. But we do require some possibly sophisticated techniques of integration to do this, like integration by partial fractions, or another more sophisticated technique like integration by parts, or integration by, say, a trigonometric substitution. So let's have a look at our first example here. Consider the ODE dy on dt is equal to 2y to the fourth plus t to the fourth all over ty cubed. So we want to first recognize that this is homogeneous and then apply the techniques we've just learned. Okay, so we set out, let f of t and y be equal to the right-hand side of this differential equation, given that we've got dy on dt on the left. Okay, so we've got f of t comma y. Now we want to substitute in, replacing t with s times t and replacing y with s times y, and check that this is just the same as f of t comma y. Okay, so we do that. F of st comma sy. So we replace the t with an s t and replace the y with an sy, and then simplify the result. Okay, so we sub those in. In the numerator, you can see that we have s to the fourth in both terms, and then we have a y to the fourth and a t to the fourth there. Okay, now in the denominator, we have an s, and then we have an s cubed. So multiply those together, and we get an s to the power 4. So if you look at the second line here of that expression, you'll see that in the numerator we have an s to the fourth, in the denominator we have an s to the fourth, so we can factorize the s to the fourth out of the numerator and then cancel that with the denominator. Now remember, we've assumed that s is non-zero, so that cancellation can carry out. Okay, and so doing so, we find that we actually have the original f of t comma y. So we've established then that f of t comma y is the same as f of st comma sy. So the equation is homogeneous. So we can continue and use our techniques for solving homogeneous equations. So first we let y be equal to t times v, or in other words, v is equal to y over t. And so by the product rule, we have v plus t v dash is equal to, and now for this part we're just replacing all of the y's in this expression here for tv. Okay, so we have 2t to the fourth v to the fourth plus t to the fourth over t times t cubed v cubed. Now we want to simplify that. So we can see that the t to the fourth there vanishes. Canceling that, we have 2v to the fourth plus 1 over v cubed. And now we know that this is going to be separable. In fact, it's going to be separable of the form that we have in equation 2. So we can rearrange this, right? So we take the v over to the right-hand side. So we have minus v there. And then we can put that all over v cubed and get a common denominator and simplify the result. And we get v to the fourth plus 1 over v cubed. Okay, so we've almost completed the separation of variables there. So what remains is to multiply by the inverse of this on both sides to put it over there with the dv, and to divide both sides by t and multiply by t and by dt. Okay, so doing so and then applying the integration symbol, we have the integral of v cubed over v to the fourth plus 1 is equal to the integral of t to the minus 1, or 1 on t, right? Which we know immediately the integral of t to the minus 1 is log of t, being the natural logarithm. So when I write log, I just leave off the base there, understanding that log in mathematics means the natural log. Whereas in high school courses, they'll often just write log to mean log of base 10, right? In a mathematics course, log means the natural log. Okay, now let's make an observation as to how to do the left-hand side of this integral. It'll be carried out by substitution, and you can kind of recognize that in the form of this integral because the derivative of the denominator is a constant times the numerator. So we're going to have a logarithm involved, but to see exactly what it is here, we would differentiate the thing that we would set out as our substitution, like the letter u. We would say something like let u equal v to the fourth plus 1, right? And then differentiate to see how we would carry out that substitution. But here I'll just differentiate v to the fourth plus 1, and so we get 4v cubed. Okay, and so inside the bracket, my u, the letter u in my substitution is v to the fourth plus 1. So I'm going to say multiply this expression here by dv, right, which is just an aid to memory of the rule of substitution, right, because these are not fractions here. Okay, so I multiply by dv in my head in aid to memory, and then I divide by 4v cubed, and so that tells me that I'm going to replace the dv with 1 over 4v cubed du, or dv to the fourth plus 1. Okay, so I can make this substitution now, and let's do this on the next page here. So having made that substitution is right here where I'm circling with my mouse. Now we need to simplify this. So you can see that the v cubed part of that cancel. We can pull the 1/4 out to the front of the integral because it's just factorization. And it's a constant, it doesn't have any v's in it. And then so we can see then that we have 1/4 the integral of 1 over u with respect to u. Okay, so that's just log of u, or 1/4 log of v to the fourth plus 1. Now I haven't included the constant of integration here because we've already put it there when we integrated the t to the minus 1. So we don't need it twice. Okay, now piecing these two together, we have log of v to the fourth plus 1 is equal to 4 log of t plus 4c, having multiplied throughout by 4. Okay, so we're nearly done. What we would really like is an equation relating just v to t, and if we can, to rearrange that to find a function, to find y as a function of t, but it's not always easy. Okay, so it follows that v to the fourth plus 1 is equal to e to the power of this right-hand side. So what I'm doing is making this equation here the exponent to base e. And when I do that, the left-hand side becomes just the inside of the logarithm function, so v to the fourth plus 1. And on the right-hand side, I have e to the power of 4 log of t plus 4c. Now I can use an exponent rule to say that this right-hand side is e to the 4 log of t times e to the 4c, and then declare a new letter, let a equal to e to the power of 4c. So that's what we do here. And then another exponent rule allows us to separate e to the power of 4 log as e to the power of log t all to the power of 4. Okay, now e to the power of log t is just t, so we actually have a times t to the power of 4. So we can rearrange this now and sub back in what v is. Remember, v is equal to y over t. Okay, so we want to take the 1 over to the right-hand side of the equation, replace v for y over t. Okay, so in the end we get y to the power of 4th is equal to a t to the power of 8 because we have to multiply throughout by t to the 4 there. Okay, so a t to the 8th minus t to the 4th. So this just gives us a curve, right? And if we actually want to find y as a function of t, well, we've got 4 solutions because we've got to take 4th roots. And not all of those are going to be real. So it's perhaps best to just leave this as expressed as a curve at this point, unless you have more information. All right, so if we had an initial value, suppose we have y of 1 is equal to 1, then we can get a particular a curve. Okay, so if we sub in t as 1, then on the right there we've got a minus 1. Okay, so that would say that a minus 1 is equal to 1 to the 4th, which is 1. So that gives us that a is equal to 2. Okay, and so we can sub in a as 2 into our expression and get a particular curve. Y to the 4th is 2 t to the 8th minus t to the 4th. Now remember, the existence and uniqueness theorem says that the solutions to this initial value problem are not necessarily unique. Right, because we may have a discontinuity at the initial value or near it, or a partial derivative not defined, right? Perhaps ambiguous. I won't go into the details of that, but I do have the solutions to the general solutions to the ODE are plotted. Those are the arrows in blue that you see for all the different values of A. But now in black we see the specific curves that we obtained, and now you know that they're not unique. Here you see we have at least 2 shown. Okay, that correspond to that particular initial value. So y of 1 is 1. So that would be here on the right-hand side. Okay, so let's move on to another example. And I imagine you must have questions, but I'll see you in the actual physical sessions. Okay, consider the ODE ty dash is equal to t plus y. Now this one looks a little bit easier. So we want to check first that this is homogeneous by rearranging so that we have y dash is equal to a function of t and y. Okay, so dividing both sides by t, we have t plus y over t, and then we set out let f of ty be equal to that, t plus y over t. So we want to verify first that if we replace t and y by st and sy respectively, that we still have f of ty. Okay, so we sub those in those places, and then we factorize the numerator and cancel the s, and we see that we still have t plus y over t. So we can declare this to be homogeneous. Okay, so next we let y be equal to tv, or v equal y over t, and we invoke equation 2. So let's have a look at this again. It's up here on the top left. We expect to get this to be separable dv over f of 1 comma v minus v integrated equal to the integral of 1 over t dt. which is just log of t, right? That's what we're expecting to get here. So we use this equation, or you could set out the whole thing again like we have here on this previous page if you wanted to. If you don't like to remember things, that's perfectly fine. Okay, so we're going to invoke that equation there. So we first want to compute what is f of 1 comma v minus v, because remember this is the denominator that we have here in equation 2. Okay, so we'll calculate that in this case. So f of 1 comma v will be just subbing in 1 for the t. So 1 plus y over 1, which is 1 plus y. But y is equal to t times v. And we've got 1 in for the t. Okay, so 1 plus v, and then take away the v, which just gives us 1, which is very, very simple there. All right, so our integral then is the integral of 1 dv over that thing that we just calculated, which is just 1. So we actually have just the integral of 1 dv. All right, now that integral is very simple. It's just v. We'll leave off the constant of integration for the time being. Now the right-hand side of that equation 2 is just the integral of 1 over t, which is simply log of t, the natural log of t. Okay, now we'll put in the constant of integration. So we have v is equal to log of t plus c. Okay, but remember v is equal to y over t. So if we multiply that result throughout by t, we'll have y is equal to t log of t plus c times t, which is our general solution to that differential equation there. Now let's again suppose we've got an initial condition and have a look at it. If we happen to have y of 1 is equal to 1, then this gives us a way to find the value of c. So remember that log of 1 is saying, okay, e to the power of what gives me 1? Well, e to the power of 0 gives me 1. So log of 1 is 0. So this part of it becomes 0. Over here we have c times 1, and then equals 1. So that says 1 is equal to c, or c is 1. So we can go ahead and sub in c as 1, and we have our particular curve y of t is equal to t log t plus t. Okay, now here in this diagram, I've displayed all of the solutions to the differential equation, right? And we don't see any equilibrium solutions there. But now when we look at y of 1 is 1, that fixes a particular curve that I've displayed in black there, which is this one here. Y of t is t log t plus t. Okay, let's move on to the next topic, which is integration by partial fractions. Okay. So we're going to digress a little bit to look at 3 integration techniques at this point. And the first one is integration by partial fractions, because we end up in this, if we go back and look at equation 2, we end up having to do some somewhat potentially difficult integrals there. Proceeding to solve homogeneous first order ODEs. And a lot of these will be by partial fractions, because we will quite possibly have a number of our integrals being products of things in that denominator once we simplify those. Okay, so let's go back and look at this technique. So the idea here, if we have something like the integral of dx over a product of linear factors, well, then we want to use the fact that to add fractions, we need a common denominator, right? So if you just look at the right-hand side of this, if you were to insist on adding that together, then you would need a common denominator, right? So you need potentially the product of all of those, right? So that's the easiest way to do it, rather than to seek out a least common multiple, is to just take the product of these and cross multiply. Well, when you have multiple of these, you end up having to multiply by, so in the first one, for example, the first summand, we would have to multiply the top and the bottom of that first summand by all of the other denominators. Okay, so we would do that, and then we do that in the second one, multiply by all of the other denominators other than x minus a subscript 2. Okay, and so on and so on. And then on the denominator you have the product here, right? And so you have one degree less in all of the numerators, and so you add all that together, and that would give you, several equations to solve for b1, b2, b3, bn, and so on. Okay, so we set it out like this because we think it's highly likely to work out that we can find the b1, b2, and so on. Okay, so then your task is to find the b1, b2, bn, so that you can then do that integral, because integrating each of these is actually very easy, right? For example, the integral of b1 over x minus a1, you would be able to pull the b1, which would be a constant, through the integral sign, and then you would have the integral of 1 over x minus a1, which is just log of x minus a1, just like what we have here. Okay, now let's have a look at an example to compute the integral of this dx over x plus 2, x minus 2, x plus 1. Well, we want to set it out just like this as a sum of three fractions. b1 over x plus 2 plus b2 over x minus 2 plus b3 over x plus 1. And now our next step is to recombine this to have a common denominator that's the product of those three functions that we have in the denominators. Okay, so we essentially cross multiply. So if we first handle the two on the right there, cross multiply those two, then we get b2 x plus 1 plus b3 x minus 2. Okay, now we've got to do that again because we need the common denominator that is the product of all three. So we cross multiply again. That would give us b1 x minus 2 times x plus 1 on the left, and then this thing that we just obtained multiplied by that new denominator x plus 2. Okay, now we have a common denominator, so our next step is to expand this and simplify. So we expand the numerator and simplify that, and we can express it as b1 plus b2 plus b3 times x squared plus 3b2 minus b1 times a single x minus 2b1 plus 2b2 minus 4b3. Now remember, we want this numerator to be equal to 1, okay? So we've got a couple of approaches from this point. So we could just observe that since we have a polynomial in the numerator and we're seeking out constants b1, b2, b3, we absolutely need that the sum of b1 plus b2 plus b3 to be equal to 0, because we don't have any x squareds in the numerator 1, which we're trying to get. We don't have any x squareds in that, so we need that coefficient to be equal to 0. Likewise, we need the coefficient of single x to be equal to 0, and then we need the constant coefficient, the last one, to be equal to 1. So that gives us three equations which we can just solve, and you can take any approach to solve that. You can even use Kramer's method if you like, that you would have learned in Math 103. Okay, or you can use a matrix method. It's fine. So those are easy to solve. So in this case, we get b1 is a quarter, b2 is 1/12, and b3 is minus a third. But doing this this part of it is often more work than necessary. So there's an alternative approach which is computationally a bit easier, which goes like this. So here's our numerator of this fraction back here that we want to be equal to 1. Now, if we just sub in something that makes each of these terms 0, then we can have a shortcut to finding those three constants, b1, b2, b3. Okay, so take, for example, when x is equal to 2, it makes this first one 0 here. right? And it also makes the third one 0. So let's sub in x is 2. So doing that, let's see what we get here. We get 0 here, we get 0 over here, and then we have 2 plus 1 is 3, and 2 plus 2 is 4. So 3 times 4 is 12. So that would give us 12b2 is equal to 1, because all the other terms are 0, and then we would just have to divide by 12, and that gives us that b2 is equal to 1/12 straight away, right? Okay, next we're going to look at the same equation and sub in x is equal to -2. Okay, now it makes the second one 0, and it makes the third one 0. All right, what does it do to this first term? If we sub in x is -2, we get -4 here, and we get -1 here, which is the product of those is 4. So 4b1 is equal to 1. And then we just have to divide by 4, and we get that b1 is 1/4. So you can see this is significantly easier than trying to solve a system of 3 equations and 3 unknowns. Okay, so we'll do the same thing when x is equal to -1, because it makes the first and the second term 0. And then we just look at the third term when x is -1. So in that case, we have b3 times -3 times +1. Okay, so b3 times -3 is equal to 1, which gives us that b3 is -1/3. So we now have each of our coefficients using a very easy way. So this gives us a means of breaking up that integral as a sum of 3 little ones. Okay, so we have 1/4 dx over x plus 2 plus 1/12 dx over x minus 2 minus 1/3 dx over x plus 1, which we can just integrate and put 1/4 log of x plus 2 plus 1/12 log of x minus 2 minus 1/3 log of x plus 1 plus our constant of integration. Now, study your log rules. Remember your log rules. We can simplify this first by making all of these fractions be over 12. Okay, so that's what I do. I introduce a numerator. 3/12 is 1/4, so I can put that 3 next to the log there. And I do that all over here with a -1/3 too. So I'm factoring out 1/12 first, so I can simplify this nicely. Now there's a log rule that says I can place the coefficients in front of the logs as exponents inside the log. And then after I do that, I can use a log rule that says the sum of the logs is the log of the product. Okay, and the difference of the logs is the log of the quotient. So I've used 2 log rules here to express this as 1/12 natural log of this quotient of these polynomials, x plus 2 cubed times x minus 2 all over x plus 1 to the 4th. And then plus our constant of integration. Okay, now I haven't quite finished, well, there was no ODE, so I didn't need to finish that. I have finished the integrals, so that's all good. Okay, now there are other forms to consider here which are a little bit more complicated. So the first one is if you have 1 over x minus a1 all squared plus x minus a2, then you can use this form. And then if we have, okay, so I think here I should have written in the last line in the denominator, instead I should have written x squared plus 1, because otherwise, you know, you can factorize this as a difference of 2 squares, and it's not quite as necessary to use this form here. Okay, so assume here I'm referring to x squared plus a1, where a1 is positive. So in that case, you would want to express your product, set it out as b1x plus b2 over x squared plus a1, right? Or you can just take a1 as negative here for this example, and then plus b3 over x minus a2, okay? Now that completes our little discussion of integration by partial fractions. It's a very brief overview. I suggest you do a lot of problems on this so that you master it in your own time, and we'll do a few in the tutorial when I see you. Okay, moving on, let's have a look at integration by parts. Now this technique, you can derive this just by remembering the product rule of differentiation. Okay, now remember that the derivative with respect to x of the product uv can be written as v du on dx plus u dv on dx. Okay, and next what you want to do is solve this equation for something like u dv on dx so that you have the rest of it as a difference on the other side. Okay, so once we have this, go ahead and think of this as if they were fractions in aid to memory of the rule and multiply by dx so that you would have u dv is equal to duv minus v du, and then apply the integration symbols so that it's just an aid to memory because those are not fractions, right? But they behave like it. So it helps you remember the rule for integration by parts, which is this line. The integral of u to v is equal to uv minus v du, the integral of v to u. Okay, let's have a look at an example or two or three. It looks like we've got three. No, hang on, we've got one, and then we've got integration by substitution, which is our last technique that we'll look at today. Okay, so suppose we've got to solve the ODE y dash is equal to x squared e to the minus x. So we want to just apply integration directly, right? Because we've got y dash is equal to a function of x there. So we integrate both sides, and it's simple to solve the integral for y here, but the difficulty is in actually carrying out the integral. So we have y is equal to the integral of x squared e to the minus x dx. Okay, now our next step here is to express one of these as a derivative, one of the multiplicand or things being multiplied there as a derivative. Okay, now you want to choose the one that differentiates to give something that's self-similar, or differentiates multiple times to give a constant times the original thing. Now, in this case, that would be e to the minus x, because the derivative of e to the minus x is minus e to the minus x. So we can express this as a derivative here, incorporating the minus sign in front to accommodate that. Okay, now in aid to memory, you can think of canceling the dx's, right? But again, they're not fractions. It's just an aid to memory of the rules of integration. So we can express this as minus the integral of x squared with respect to e to the minus x, which you can think of as your u, your letter u there. Okay, now if we set this out as u, then we can just directly apply this rule here of integration by parts and say that this here, this part of it in brackets, right, pulling the minus sign out in front, we can say that that's x squared e to the minus x, or uv, vu, and then take the integral of v du. All right, so in this case, we're swapping these around. So this is our v in this case, e to the minus x, and then with respect to x squared. But we can introduce a dx there. So we sort of think of this temporarily as if it were a fraction and introduce a dx. Now you could see that it would cancel if there were fractions, but it's just in aid to memory of the rule that we can make this substitution here. And so we can treat this part as dx squared over dx. We can treat this as a derivative at this point because it is a derivative. All right, so the derivative of x squared with respect to x is just 2x. So we can replace this with 2x, meaning that we have the integral of x e to the minus x with respect to x, and we just have pulled the 2 out the front of that integral because 2 is a constant. Okay, now we've got to repeat the technique again because we've got the same situation, but you'll notice now that we don't have the integral of x squared e to the minus x. We now have the integral of x e to the minus x, which is a little bit easier. Okay, so we apply the same technique of integration by parts on this again, representing this as the integral of x with respect to e to the minus x, because we've again treated this as a derivative, replaced this with a derivative, and then made the dx substitute away. So that introduces a minus right there. Okay, now we use the technique of integration by parts here, separating this as uv minus integral of v du, and this is what we have. Okay, so now we've got some simplification to do. We expand the minus 2 in, and then we take the integral of e to the minus x, which is just minus e to the minus x, and then we've got two minuses there to cancel. Okay, so we got that, and then we can simplify that. Now they will all have an e to the minus x common there, except for the constant of integration, right? So in the end we get y is equal to minus e to the minus x outside of x squared plus 2x plus 2, and then plus our constant of integration. Okay, so that was a very tricky one, and that's the only example I'll give you for now of integration by parts. Again, I suggest you do several examples of your own, and there are lots of books out there that have problems on this. Many of the, say, secondhand high school books that you find in a secondhand shop on Maths B and C will have plenty of examples like this. So maybe pick up one of those for a couple dollars or less, and practice some problems, or find a source in the library. Okay, so now let's have a look at an integration by substitution, or a couple of these. Now the difficult ones are integrations that require trigonometric substitutions, or something like a cosh or a sine function, right? The hyperbolic functions that behave a lot like sine and cos, so hence they're called sine and cosh. Okay, so to solve the ODE, square root of 9 minus x squared times y dash is equal to 1, we can see that it's separable, but it's difficult because we have to integrate 1 over the square root of 9 minus x squared. So how do we do this? Now this is inspired by the fact that sine squared plus cos squared is equal to 1. Okay, which gives you a hint on what substitution to make. So we let x be equal to 3 sine of theta. Okay, why 3 sine theta? Well, because 3 squared is 9, and that allows us to pull the 9 outside the square root there. So let's differentiate that expression, and take dx on d theta. So we get 3 cos theta. So that suggests the substitution, replacing dx with 3 cos theta d theta. Okay, so we do that next. We have 3 cos theta d theta there, and now x is equal to 3 sine theta, so we sub that in, and we have in the denominator we have the square root of 9 minus 9 sine squared theta, or and so, okay, we can factor out the 9, but when we take the square root we get a 3. Okay, and then what remains inside the square root is 1 minus sine squared, which we know is cos squared, because sine squared plus cos squared is 1, which is the whole reason we set out this particular substitution to start with. Okay, so we can see we have the same thing here in the numerator as we have in the denominator once we take that square root of cos squared. So this becomes the integral of 1 with respect to theta, which is just theta plus c. Okay, now what is theta? Well, we would have to solve this original x equal 3 sine theta for theta, right? But that's actually easy. We divide by 3, so we have x over 3 is equal to sine theta, and then we apply the inverse function to both sides of sine, and that's called arc sine, or on your calculator you'll see sine and superscript minus 1 to mean the inverse function, or arc sine. So we would have arc sine of x over 3 and then plus c. So this is equal to y. All right, now let's move on. Let's simplify the integral x dx over square root of 1 plus x to the 4th. Now this is probably the hardest example, and it's a good one because it forces you to see how you might need sometimes some hyperbolic functions. Or does it? Actually, maybe that's the next example. Let's see. Okay, so first we let u be equal to x squared. Okay, simple enough. Differentiate, we get 2x. So that tells us to perform the substitution replacing dx with du on 2x. So that gives us the integral 1/2 1 over square root of 1 plus u squared du. Okay, yes, I think we still need a hyperbolic substitution here because we're not done. You see it's easier, but we're not yet done because we still have a square root of 1 plus u squared. Now it's not a difference, it's a sum. So in this case, we're going to want a hyperbolic function as a substitution. Okay, now these are defined as follows, and you'll need these functions a few more times in this course. So let's let cosh of x, as it is defined, to be 1/2 of the sum of e to the x plus e to the minus x. And sine of x is half the difference of e to the x minus e to the minus x. And I always forget which one is which here. So sometimes you need to look it up. Okay, so in this case, let's let u be equal to sine of v. And again, we want to differentiate so that we can see how to replace the u with a dv. So the derivative of sine is cosh, and you can just check here, differentiate this top line, equation 3, you'll actually get equation 4. So the derivative of sine is cosh, just like the derivative of sine of theta is cos of theta, right? So that's why these are named like they are, because they behave a lot like sine and cos, but not exactly like them. Okay, so we should make the substitution replacing du with cosh of v dv. Now we also need another identity, that 1 plus sine of v is equal to cosh of v, which these are the details of deriving that identity. Now remember, sine squared of theta plus cos squared of theta is 1. So this identity is indeed similar to that. It says actually cosh squared minus sine squared is 1, right? So it's a difference. And in fact, that's in a hyperbolic form, right? So the hyperbolic form is x squared minus y squared is equal to 1. Whereas sine and cos have a circular form, cos squared plus sine squared is equal to 1, which corresponds to x squared plus y squared is 1, or a unit circle, right? So that's why we call these hyperbolic functions, because of that hyperbolic relationship there. Okay, now we're ready to simplify the integral. We've already replaced x over square root of 1 plus x to the 4th with 1/2 1 over square root of 1 plus u squared. Now we're going to replace the u with sine of v. Okay, and we also replace the du with cosh of v dv. So we get cosh of v in the numerator. We get the square root of 1 plus sine squared in the denominator, which we can simplify by this identity here and say that the square root of 1 plus sine squared v is just equal to cosh v. So we've got cosh v over cosh v, which was what we were hoping for in that substitution. So we actually get the integral of 1 dv, which is super simple, right? It's just we just have 1/2 v plus our constant of integration. Okay, now finally we need to replace the v with what it was in terms of u. So we need to then solve our original setting out of letting, where was it, up here, u equals sine of v, right? So we apply the inverse sine function, which we can call arc sine or r sine. I don't actually remember which way it's supposed to be said or written, but I mean the inverse sine function here applied to both sides of this, setting out u equals sine of v. So v is equal to the inverse sine function of u. Okay, so we have 1/2 inverse sine function of u plus c, but u, remember, was just x squared, so our integral is 1/2 inverse sine of x squared and then plus our constant of integration. Okay, now was that a differential equation? No, it was just an integral. Okay, good. Now, I think this is our last example here before moving on to the next section. Here's another example in which we're going to use a hyperbolic function. So here we see a first example of a second order ODE. Why is it second order? Well, because the highest order derivative is 2 here, what we see on the left. Now over here on the right we have a derivative squared, but that makes it just nonlinear. Okay, so it says solve this ODE where absolute value of the first derivative of y is less than 1. Okay, so let's let u be equal to that first derivative dy and dx, so that we can just look at solving the simpler first order derivative, but you see here it's nonlinear because we have a nonlinear power here. There's a square there. Okay, it's separable, so it's fairly easy. So we can reflect on our techniques for separable equations here. We divide both sides by 1 minus u squared and put the dx over on the right, apply the integration symbols, and then we've got to integrate. So the right-hand side is super easy. It's just x plus c. But the left-hand side gives us a bit of a headache here. We've got an integral of 1 over 1 minus u squared. So this time let's what are we doing here? We're going to let u be equal to the quotient of sine over cosh, which we call tanh. Tanh of u is sine over u cosh over cosh of u. Okay, so we want to differentiate and find out how we're going to make our replacement here. Okay, so the derivative dy on dx is tanh of x plus c. Now we put y is equal to the integral of tanh. Replace tanh with sine over cosh. Now observe that sine is the derivative of cosh, and so we actually have the integral of 1 over cosh with respect to cosh, which is log of cosh of x plus c, and then we need a new constant of integration there. So there are multiple solutions here, but since we have absolute value of y dash less than 1 in our problem description, we can throw one of those away. We can discard the solutions y is equal to plus or minus 1, which are actually solutions to this differential equation there. Okay, so that's all for now. See you in the next one.